Everyone, welcome back again. We're continuing chapter 8 2 homework, and this is going to be problem 7, which is going to be 3 parts. And I just realized that I didn't leave a lot of space for part C down at the bottom right there, so give me just a second and we'll see if we can fix that. We'll do that. There we go. Everything's a little bit smaller, but that's all right. Okay, so problem number 7. Like I said, it has 3 parts, and the first part, well, let's just go ahead and read it first of all. We have a 65 kilogram bicyclist and an 8.8 kilogram bicycle. All right, so the mass of, let's see, cyclist, and I'm going to put C for the cyclist is 65 kilograms. Okay, I'm going to do mass of B for the bicycle itself, because otherwise they have the same letter, is 8.8 kilograms. And so the initial velocity equals 14 meters per second. Okay, by the way, that right there, let's just do a little bit of extra math. We don't care how much the bicyclist or how massive the bicyclist is, or the bicycle. We care about how massive the whole system is, right? Because we're talking about bringing the bicyclist or the cyclist and bicycle system to a rest, and so that whole system we've got to bring to a rest. So what is that if we add them together? Well, that should be, what is it, 73.8 kilograms. All right, so let's just go ahead and do that right now. What are we doing? We're bringing them to a stop. All right, well, you can infer that that means the final velocity equals 0 meters per second. All right, and brakes work on the principle of friction, right? Here's our bicycle right here. Here's our bicyclist sitting on the bicycle, and I guess it's not too bad of a bicycle. And friction, brakes, that is, act against the direction of motion. All right, so we can pretty much assume, as the answer tells us right here, that the work that is done is going to be negative. All right, it's opposite the direction of motion, because here's the distance that the bicycles are traveling, and the brakes are working against that. All right, but we're also going to kind of prove that with the work kinetic energy theorem. That is, work being a change in kinetic energy. All right, so we want to find how much work is being done. So, all right, let's take that and let's find out the work that is done by the brakes. Work done by, I want to call it B, but that doesn't make sense. How about F? F for friction. Work done by friction, that is the brakes, equals our change in kinetic energy. That's our work kinetic energy theorem. All right, so let's expand that out a little bit. What's a change in kinetic energy? Well, that's kinetic energy final minus kinetic energy initial, right? And so the work done by the brakes is, what's the final kinetic energy? Well, if the velocity is 0 and kinetic energy is inextricably tied to velocity, then that means that whole final kinetic energy is going to be 0 joules, right? So the first part of that is 0. It's coming to a stop. It has no more kinetic energy. But the initial kinetic energy is what? Well, we know that's 1/2 mv initial squared, right? It looks like it says OJ right there. Sorry, it's 0 joules. So it's 0 joules minus 1/2 times, what's the mass of the whole system? All right, well, we added those together. That's 73.8, right? 73.8 kilograms times the initial velocity, which is 14 meters per second, and that's going to be squared, right? Because the velocity is squared. That's why velocity plays a big part in an object's kinetic energy. Not so much the mass, but the velocity. All right, so what is the work done by friction, or that is by the brakes? All right, we can see already that that's going to be negative, because you've got 0 minus something. So 0 minus 0.5 times 73.8 times 14 squared, I get 7,000, negative 7,232 joules. All right, and that's exactly what we're predicted right there that our answer is going to be. And it is negative because you've got your final kinetic energy minus your initial kinetic energy. Remember, a change in something is always the final minus the initial. So that works out, and it's a good application of our work kinetic energy theorem. All right, so let's look at part B now. Part B is asking us, how far does a bicycle travel if it takes 4 seconds to come to rest? All right, well, time is brought into this. And if you look back over your notes and work in kinetic energy, time isn't really figured in. So it sounds like we might need to bring kinematics into this. Let's just go ahead and start by writing down everything we know. All right, our time that this takes place equals 4.0 seconds. The mass of the whole system is, what was it, 73.8 kilograms, right? And the initial velocity was 14 meters per second, and the final velocity was 0 meters per second because it's coming to a stop, right? And what we're asked to find is, what is the distance, all right, that takes place in. All right, well, what we can do is we can find out, based on the amount of work that is done right here. Here's our work that is done. We can tie that to a force, and the force applied on the mass of the bicyclist can be tied to the acceleration. Now, here's what I mean by that. If we know that this right here, this work, which is right here, right, equals a force times a distance, and it's really that distance that we're trying to find. And a force is a mass times acceleration times the distance. And we know time, and we know initial velocity, and we know final velocity. We should be able to write in some sort of equation for acceleration that stands in there using all the things that we know, so that we can solve for distance. All right, so let's look and see what we have. With regards to kinematics, we've got time, we have initial velocity, final velocity. We do have an equation from kinematics that goes as such: v final equals v initial plus acceleration times time, right? We know the v final, we know the v initial, and we know the time. And so that if we turn that around and solve that for acceleration, acceleration is v final minus v initial divided by time. We now have something that will stand in here. And we know the mass, so we know the force, and therefore we can solve for the distance because we already know the work that is being done. Okay? So, we can say the work equals force times distance. And so the force is going to be mass times acceleration times distance. And of course, I'll erase that other thing right there. All right, and of course we want to solve for distance, so we can say that distance traveled is going to be the work that is done divided by the mass times acceleration. Okay, again, this is taking our work and energy and our kinematics and tying them together through acceleration. All right, I'm going to move this up here because we have a little more space. Okay, so the distance that is traveled is the work. We know that. That is, oh, you know what? I'm going to write this one more way, and write one more general equation, and then we'll substitute in. Okay, the work we know from the previous part of the problem divided by the mass times what's the acceleration. That's why we did this right here. So we have an equation that stands in for the acceleration because we know every other part of that. All right, so it's v final minus v initial over time. That is our acceleration because we substituted that in. Okay, now we can actually solve for our displacement, or our, well, you might say our distance. Okay, the work that is done equals what is it? Negative 7,232 joules, right? And that's going to be divided by what's the mass of the system? That is 73.8 kilograms, and that's going to be multiplied by this whole fraction right here, which you can do. The v final is 0 minus v initial. V initial was what? That was 14 meters per second, right? 14 meters per second. And the time that it takes is 4.0 seconds. Again, this whole big fraction right here is really standing in for acceleration. And of course, this is our mass and this is our work, and we can use it to solve for what the distance is. So, what is the distance that is traveled right there? Negative 7,232 divided by the quantity 73.8 kilograms times, hey, look at this, that's going to be negative, right? Because it's 0 minus something. So negative over negative is going to be a positive distance. What is that positive distance? If I calculate that out, that gives me 28 meters. All right, and that's exactly what we were told right here at the outset. That's what we expected. So, that's our distance. So we have our work that is done. We have our distance that is traveled. And so the last part of the question is actually going to be pretty easy. The question is, what's the magnitude of the braking force? All right. So we know that work that is done equals force of, I want to call it braking, but I'm going to call it friction. What is the friction force? All right. Work is force times a distance times the cosine of the angle between them. Right? Well, the angle between them is going to be 180 degrees, right? Because the distance is this way. The force of friction, I'm going to write this up here, the friction force is acting against it. So it's going to be a 180 degree difference right there. So we can just rearrange that and solve for our force. The force of friction is going to be work divided by d times the cosine of, what's that angle between them? It's a 180 degree angle between them right there. So cosine of 180. We know that's going to be -1. So what's our work? That is negative 7,232 joules. And our denominator is going to be our distance, which we just found to be 28 meters, times the cosine of 180. That doesn't really change anything other than the fact that it makes the denominator negative. And if the numerator is negative, then we have a positive total force. It's just applied in the opposite direction. By the way, you can't have a negative magnitude force. You can have a force in a certain direction, but it can't be a negative magnitude. So what is that magnitude? Negative 7,232 divided by 28, I get 258 newtons. So I realize that our answer right here is 260, and I'm trying to figure out why that is. I think that may be, well, it may be a matter of rounding. If we use the whole number 7,232, or if we used, I think the original value of that was 7,232.4. So that may have been used to calculate this right here. So that's a rounding issue. All right, sorry for that discrepancy, but it's pretty darn close, and that's what we expect. So again, this is this problem is a good application of the work kinetic energy theorem, also relating work and energy to kinematics, and also going back to our main equation for work being force times some distance. So there you have it. It's problem 7 on homework 8.2. Please make sure you come see me if you have any questions, and in the meantime, I'll see you on the next one.